Okay, so here I want to explain this equation 5 137. I think it says like that, 5 137. Yeah. So last time I told you that why it is cofactor, or in what sense it is cofactor. Okay. But let me see. Let me just analyze this equation. Maybe left-hand side. So first of all, this is the matrix element. Yeah. Okay. This is the matrix element here. So this is a matrix element for F. Yeah. I think as we discussed last time. So this matrix looks like this. So we have x1, x2, partial 1, x3, partial 2, x1, partial 2, x2, partial 2, x3, partial 3, x1, partial 2, I'm sorry, this is partial 3, x3, no, x2, partial 3, x3, sorry, x3, yeah, x3, and this determinant. I think this is the determinant we are thinking about now, okay? So then, if I look at this very carefully, you can first pick I. I is kind of independent. So I, for example, consider 1, yeah? Just 1, okay? Then there is a summation, as we discussed. So J here is summation, right? And another summation is K. K is also summation, right? And then there is a beta, beta, gamma. This is not summation. This is not summation, right? So we can choose, for example, beta, gamma, maybe. So what about beta equal 1, gamma equal 2? Okay, so then that means this one. This is beta. No. I'm confused. Beta equal 1. Okay. Let me do this. Let me just. We do choose like this. So beta equal 1, then beta equal 2. See, we are like ending up choosing 2 rows. Am I correct? So because we choose beta equal 1, gamma equal 2. I don't think we can choose the same. I don't know if we can choose, for example, beta equal gamma equal 1. That's a problem. But from this side, if I look at right hand side, we cannot choose this, yeah, because alpha has to be different from beta. Sorry, beta has to be different from gamma. Alpha has to be different from gamma. From right hand side. But left hand side, I don't know if I choose. But let's choose I equal 1. We also chose I equal 1. Hey, I think I'm wrong. Am I wrong? I don't know. It's I equal 1. So we also chose I equal 1. That's this one. We chose I equal 1. So JK are not 1. From here, J shouldn't be 1, K shouldn't be 1. So we have to this part, yeah, this part, JK not 1. So it's from here. Okay, so anyway, you can see here. Now I chose this way. See, IJK beta equal 1. I chose beta equal 1, gamma equal 2, right? Then we have a summation, JJ. So J goes to 1 or 2, 2 or 3, okay? So we can have beta, this is 1, this is 1, X 1, partial 2, no, J has to be 2 or 3. J has to be X2, partial 2, gamma 3, no, X3. Yeah, this one is this. Then we have minus sign because we have switching. Now J is 2. No, sorry. This is beta is 1. So J is 2. No, J is 3. Gamma is 2. K is 2. And see, this is beta, gamma, beta, gamma. So it always has beta equal 1, gamma equal 2. Beta equal 1, gamma equal 2, beta equal 1, gamma. But J and K can be 2 or 3. So this is J, K, J, K. Then this sign comes from epsilon 1, 3, 2. This is minus 1. So this thing is a cofactor of something. See, 1, 2, 2, 3, 1, 2, 2, 3 minus 1, 3, 2, 2. Is this strange? 1, 2, 2, 3. Then 1, 2, 2, 3. 1, 2, 2, 3. 1, 3, 2, 2. 1, 3, 2, 2. So this is the cofactor of this. Very interesting. So, conclusion is this is a cofactor. This should be like F I alpha. So this is different. F alpha I cofactor should be this. Makes sense? Let me try. Okay, let's do 1, 1. If we consider 1, 1, this is 1, 1. So the cofactor should be like this. 2, 2. This is a cofactor. Okay, we do here. This is 1, and this is 2, 2, 3. The problem is this can be 2, 3 or 3, 2. See, actually, I don't remember the sign of cofactor. Cofactor. This is a cofactor of something. Cofactor include sign. Cofactor include sign. Cofactor include sign. Okay. So the question here is, JK has to be 2 and 3. JK. So I think this is okay. This JK. So there is a rule to choose. So there has to be a table like this. IJK. I is okay, but alpha. See, there is a such table. If so, you have alpha, beta, gamma. So you have, if you choose 1 for alpha, beta has to be 2, gamma has to be 3. If you choose alpha to be 2, beta has to be 3, gamma has to be 1. If you choose alpha to be 3, beta has to be 1, gamma has to be 2. So let's try this case. So now we consider 2, 1. What is the cofactor for 2, 1? This is 2, 1. Okay, so the cofactors 1, 3 minus 1, 2. Okay, this has to be the cofactor. This way. This has to be cofactor. So let's see. We consider this is 3, 2. No, 3 and 1, right? So partial 3x2 partial 2 x3. This is epsilon 1, 2, 3. This is plus 1. Plus epsilon 1, 3, 2. This is minus 1. Then you have partial 3 x3 partial 2 x2. 2, 3, 3, 2, 2, 3. 3, 2. This is strange, right? What is wrong? We chose alpha 2. And this is 1. I'm sorry. So this is 1. Partial 1 x3 partial 1 x2. 3, 2, 1, 3. So this is more like this. 3, 2, 1, 3. This is minus. This is 1. And 1, 2, 3, 3. This is 2. 1 minus 2. Yeah. 3, 2, 1, 2. Sorry, I'm confused. 3, 2. Why there is 2? 3, 2, 1, 3. 3, 2, 1, 3. 3, 2, 1, 3. Okay. 3, 2, 1, 3. 3, 3, 1, 2. 3, 3, 1, 2. Okay, this is okay. 1 minus 2. Strange. IJK. 1, 2, 3. This doesn't include sign, right? 3, 2, 1, 3. Okay, I think this includes a sign. Because this is see, you can see this is equal minus sorry, minus 2 minus 1, right? And this minus actually comes from minus 1 to the power 1 plus 2, 2 minus 1. So this is exactly cofactor. This is a cofactor to 1. Okay. Okay, okay. I think this makes sense. Yeah. So please, actually, I would like everybody to check this is indeed correct. So this equation I now delete to make a conclusion clear. This equation here is the equation for cofactor this. But then there's a rule for beta and gamma. This is this has to be a circular permutation. Okay, so if alpha, so beta, you have alpha if you need this table. If your alpha is 1, beta is 2, gamma is 3. If alpha is 2, gamma is 3, beta is 3, gamma is 1. If alpha is 3, beta is 1, gamma is 2. So you need this table, you know, to decide beta and gamma. Okay. Then you don't need anything else. So for this index, you can choose anything for alpha I, something like this. So I can be 1, 2, 3. Alpha has to be 1, 2, 3. Yeah. So you can specify all 9 cofactors. 9 cofactors. Only the ambiguity is what is beta and gamma. And beta you can decide from alpha value. If alpha is 1, beta is 2, gamma is 3. This has to be 2, 3, 1. See, this has to be follow 1, 2, 3. This way. If you start from 2, then beta is 3, gamma is 1. If your alpha is 3, beta is 1, gamma is 2. Then I can be anything. I can be anything. And J is a summation. J and K are summation. So J, K, you have to consider all combination for JK. So for JK, you have 1, 1, let me see. You have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, 3. So you have 9 combinations for JK. But for beta gamma, it is uniquely decided if the value of alpha is given. Yeah, beta and gamma is decided from the value of alpha. So this is a cofactor. I hope you understand. If you don't understand, please give me some message through the form or whatever. Okay, so what is the time? We have 30 minutes. So maybe let's go next section. Change of area. Okay, we consider element of area dA in the undeformed configuration with unit normal n. Vectorial representation for this area element is this. Okay, so you just have some area with with the size of dA, then you have some normal vector. So this is called this. Okay, but then in this representation, the direction of n is not unique. Okay, so direction of n can be this way. So this is also a right angle, and this is also a right angle. So, however, if A is viewed as a vector product of two material elements, dx and dx star in the form, yeah, this way, so if you consider dA instead of these two vectors, dx and dx star, and this parallel, how to say, parallel shape, square, and if you consider this to be dA, then the direction is uniquely decided. The normal direction is this way, okay, because we decide the direction, normal direction by cross product. Dx multiplied by dx star. So then if you write this in this notation, E alpha beta gamma notation this way, yeah. So dA alpha. It's a little bit confusing. Is it okay? Deformation of body maps dx onto small dx and dx star small large dx star onto d small x star, and the deformed elements form the area. This way. Using a cofactor expansion, we get with a cofactor expansion. So what I said, I think what I say here, this is just Eijk. Yeah, so then we use if we use cofactor expansion, which is see ijk beta j gamma k. So ijk beta j gamma k is alpha beta gamma j I alpha. Isn't this strange? So this whole thing has to be this way. This thing has to be epsilon, alpha, beta, gamma, if I remember correctly, J, I alpha, J, partial I, X alpha. Is it partial or this is partial I, X alpha? I think it is okay. Because see, you replace epsilon, you replace this beta, x beta, and d epsilon. So you replace this whole thing to this one, right? Then we have j go to here, partial I, partial alpha goes to here. So this is okay. So this is we can obtain this by using cofactor expansion. This relation has as its inverse dA large A alpha equals small j partial alpha xi d small ai. So we should understand just by analogy. I'm sorry, I don't think I can prove this. We do this. We will understand this by analogy. Please understand using analogy. Okay. Because small letter go to large letter. Second ijk go like alpha, beta, gamma. So this interchange. You just interchange large letter to small letter, ijk to alpha, beta, gamma. You obtain this relation without proof. Okay, so I think I finished up to 5.7, 5.6. So then next video, I will move to chapter 6, this motion part. I hope this is easier than before. Okay, so I will stop now and see you later.